Okay, let's talk about something that can feel like a total black box on our bikes, the electrical system. You know, it's kind of like your bike's nervous system. You don't really see it, but it's the reason your lights turn on, your horn beeps, and your engine fires up. So today, we're going to pull back the curtain and make sense of it all.
So here's the game plan for our journey. First, we'll get the big picture of what this nervous system is all about. Then, we'll break down the three fundamental forces that make electricity work. After that, we'll look at the one golden rule that connects them all. We'll see how power actually gets around in circuits, and finally, we'll meet the key components that are doing all the work.
You know, for a lot of people, seeing a big bundle of wires is enough to make you just walk away and call a professional. But the goal here is to switch that feeling of, I have no idea what's going on to, okay, I get this. Because honestly, once you get the logic behind it, it's not nearly as scary as it looks.
I mean, we've all been there, haven't we? You go to hit the horn, and you get this sad, weak little meep instead of a real blast. Or you notice your headlight just doesn't seem to be cutting through the darkness like it used to. Well, those aren't just random glitches. They're clues. And by the time we're done here, you'll know exactly what those clues are pointing to.
To figure out what's going on, we first need to learn the basic language of electricity. And it really all boils down to these three concepts. Think of them as the ABCs. Get these, and everything else we talk about will click into place.
So first up, we've got voltage. Voltage is the potential power. It's the push, the pressure that's just sitting there, waiting to move the electricity along. The absolute best way to picture this is to think of a big water tank. All that water sitting in there is creating pressure ready to burst out. That pressure, that's your voltage.
Okay, so if voltage is the pressure in the tank, then current is what happens when you open the tap. It's the actual flow of electricity moving through the wire, doing the work. In our water analogy, it's the stream of water shooting out of the pipe. That's the current, measured in amps.
And then there's the third piece of the puzzle, resistance. Resistance is anything that tries to stop or slow down that flow of current. So if we're thinking about our water pipe, resistance would be a nasty kink in the hose or some gunk that's clogging it up, making it harder for the water to get through.
And this little table just brings it all together perfectly. Voltage is the water pressure, and we measure it in volts. Current is the water flow, measured in amps, and resistance is the blockage in the pipe, measured in ohms. Seriously, if you can just remember this simple water analogy, you're halfway to diagnosing almost any electrical problem on your bike.
Okay, so we've met our three main characters, voltage, current, and resistance. But how do they all work together? Well, it turns out there's one simple, beautiful rule that governs their entire relationship. It's called Ohm's law, and it's basically the electrician's golden rule.
And there it is. Voltage equals current multiplied by resistance. V equals I times R. This little formula right here is the master key. It tells us that these three things are always connected in a predictable way. If you change one, the others have to change to keep the equation balanced.
So why should you care about some math formula? Well, here's where it all comes together. Let's go back to our dim headlight problem. That little bit of corrosion on a wire, that's our pipe blockage. It increases the resistance. Now, according to Ohm's law, if the resistance goes up, something else has to go down to keep things balanced. And that something is the current. And less current means, you got it, less power for your headlight and horn. See, it's not some random gremlin, it's just physics in action.
We've got the forces, we've got the rule. But how does the electricity actually make the trip from the battery all the way to your taillight? It travels on special pathways, which are called circuits. Think of them like the roads and highways for electricity. Now, there are really two main kinds of roads. The first is a series circuit. Here, everything's connected in one single loop. It's like those old Christmas lights where if one bulb burns out, the whole string goes dark. Yeah, not exactly what you want on a motorcycle, right? That's why our bikes use parallel circuits. In a parallel circuit, every component, your headlight, your horn, your signals, gets its own separate path to the battery. So if one bulb blows, everything else stays on. It's way more reliable and a whole lot safer.
All right, we know the rules of the road and the types of highways the power travels on. So now, let's meet the actual hardware. These are the key players in the system that make all of these principles work every single time you turn the key. And of course, we have to start with the heart of the whole operation, the battery. It's basically a little box of chemical energy that it converts into the 12 volts of electrical pressure your bike needs. It's what powers your lights and everything else when the engine's not running. And here's a huge tip. Ever see that crusty white or greenish powder on the battery terminals? That's corrosion. And what does corrosion do? It adds resistance. And now we know exactly what that means for performance. So keep those terminals clean. Next up is a tiny little component that honestly doesn't get enough credit. It does its most important job by literally destroying itself.
This little guy is probably the single most important safety device in your entire electrical system. Let's meet the unsung hero, the fuse.
So here's how its heroic sacrifice works. Let's say a wire shorts out, causing a massive, dangerous surge of current. Before that surge can do any real damage, the tiny little wire inside the fuse melts in a fraction of a second. Pop. The circuit is broken, and the flow of electricity stops dead. The fuse is toast, but by sacrificing itself, it just saved your bike's computer or wiring harness from getting completely fried.
And this brings us to an absolutely critical, non-negotiable golden rule. Never, ever, ever replace a blown fuse with a piece of wire or a gum wrapper or anything else. The fuse is designed to be the weakest link in the chain. If you bypass it, you haven't fixed the problem, you've just made it so the next most expensive thing is what blows up. And that could be a disaster.
And last but not least, let's meet the system's bouncer, or maybe its traffic cop, the diode. A diode is basically a one-way street for electricity. It lets the current flow in one direction, but it slams the door shut if it tries to go the other way. This is super important for things like your charging system, making sure power can get into the battery, but can't leak back out when you turn the bike off.
So there you have it. From the basic forces of voltage and current to Ohm's law, circuits, and the key players like the battery and the fuse, your bike's electrical system isn't some unknowable black magic. It's a logical system that follows clear, predictable rules. So now the question is, with all this new knowledge, what's the first thing you're going to go investigate on your own bike? Are you going to check those battery terminals? Maybe pop open the fuse box for a look? That journey from intimidation to confidence, well, it starts with that first curious look.